Hello everybody and welcome back. In this video solution, let's talk about how to implement prefix trees. First things first, why even think about a different data structure? Let's take the case of auto-completion, and this is what I've implemented over here. This is what we see. LEE are the three characters that I inputted to my search bar, and my browser somehow auto-completed it to leetcode.com and showed me a couple of more different cases I want to search for. LeetCode top 100 Google questions or my own profile. These are all of the things that I've searched for in the past. Now, how does my browser do this? Well, one possible implementation of that could be that LEE is present in a dictionary and it is present as a key. And corresponding to it, there could be multiple values, leetcode.com, my own profile, or top 100 Google questions. But what about LE? If I removed one character and I just had LE, my browser should still be able to give all of these. And what about leet? That should also give me all of these three. We clearly see that there is a lot of redundancy in this kind of structure we have. And so we're looking for something that is better, that is able to say that all of these words have the same prefix. And we want to exploit the property of having the same prefix. Let's start from a very basic case. Let's say that we have the word AX given to us. The first thing we'll do is split it out character by character. And so let's have a look at the first character A. And we'll go inside of the tree and we'll create a node for A that contains all of the information of A. Then we look at the next character, which is X. And so now we somehow want to continue the information of X from A. So we had A over here. And now we want X to follow it. And so we'll make X a child of A. Now X also marks the end of this particular word. So we'll mark it with an orange line at the bottom, saying that at this point, we're completed with this word. Let's add another word to it. Let's say the next word is app. So how do we go about it? The first thing we want to do again is iterate over all the characters and try to add them one by one. The first thing we'll do is look at the character A. And what do we realize? A is already present inside of this data structure. And so we don't need to create another node. We'll just continue from what it was. And we'll set P, which is the next character, to be a child of A. And so A now has two children, X from the previous case and P from this current case. Now P is not alone. There is another P in the next iteration that comes up after it. And so we'll have P added as a child of the previous P. At this point, we'll again mark the end of this word. This is fine. Let's try to add another character, another word, apple. You'll realize that APP and apple share this big prefix with them. So we don't actually create APP, another sort of structure like this for apple. We just use the APP and we'll add L and A to it. Note that we don't change this guy. We still want to keep the information that there was a word like APP which ended at this point. Now we have another word apple which ends at E. So we'll mark it E as well. And this way we can also add the word API. I marks the end over here and we have this kind of structure. At this point we can be sure that this will work. We have removed all of those redundancies. We are marking the end of word and we know what children are and how nodes function. So we can jump into the code for this part. Let's implement a class called node. And I'm just going to steal from this. And what all values should it have? First of all, we want to know what the character itself is. Is it A? Is it X? Is it P? Then we want to know who all its children are. So we'll create a dictionary for that. And we also want to know at the end if this is an ending character or not. Look at how we marked X to be the end, I here, P here, and E here. We also want to know, okay, does this character mark the end of a particular word? So we'll set it to false, we'll set it to end, and we'll have it passed over here. So we'll have it pass C and end. And we'll set it by default to be false because that's more convenient for us. Okay, we're done with the creation of this node. Let's quickly talk about how to initialize this tree because now we can finally jump into creating the tree itself. There's one very small issue that we need to fix first. Let's look at this case. I have all of the 4 words from before, but another word BB added. Now BB should exist its own component, right? But earlier we only had A as the root of the tree. Now BB demands another B as the root. Now instead of messing with all of these guys, let's just create a dummy node with the character of hash. This is just for implementation reasons, since this can have all of its children as A, B, C, D, E all the way up till Z. This should simplify a lot of our implementation. So let's create first of all a root node, which is going to be a node with the character of hash. Now the ending is going to be false because we are expecting this tree to be big. So the end is false, and this is by default, so we can just write it this way. Cool, we're done with the setup. Now, how do we insert elements into it? First, let's create self.current equals to self.root. I basically want to keep the root as is so that I can have current pointing to the root, and then current can sort of travel the tree as we want. So current is the copy of root without disturbing the root itself. Now we want to iterate over all the characters in the word. And for each of the character, I want to have self.current child as C, right? I'm going to access this guy, and I want to say that this is a new node with the value of C inside of it. What I'm essentially doing is I'm saying that self.current.child, which is the hash value, is going to have inside of the dictionary child, which you can see over here, one particular key as C, and that is going to correspond to a node of C. So the entire structure is something like this. Let's say that the first character that we encounter is A. So we have A colon the value. Now what is the value going to be? It's going to be a tree node in itself, and it's going to be a node of A. This is sort of the idea behind it. Now why do we do this? That's because in the next iteration, I want to set the self.current to be self.current.child of C. Basically, once I have considered the character A, I want to move to this node and set it as the current node. So I was at this node, one of its child was here. Okay. And now I want to move this current to the value of the child, so that now I can again consider its child, then move here and then consider its child, and then on and on and on. One quick implementation level detail is that this self.current.child of C may not always be present. So in case if self.current.child, if C is not present in this, if the key is not present inside of this dictionary, let's create a value for this. So we'll do node of C over here. And if it already is present, then we won't disturb it, right? Because let's say in the first case, we had to create this A and X. But when we come on to APP, once we have already done AX, then we don't want to recreate this A again. We want to use the previously stored one. Okay. Also at the end, we want to set the self.current.end to be true, saying that this current guy, whoever I am at, is going to mark the end of this word since we are done with the iteration of it. Okay, I want to do a quick sanity check, and this is generally a good idea to do, especially since we are testing this out. So let me just try to insert the word apple into it, and we'll see what happens. If there are no syntax errors, that should work. Cool, this works. So now we can move on to implementing the starts with function. I'm going to implement that first because the search function is just going to build on top of that. Like there's one single line that's going to be changed. Okay, now how do we detect whether we are starting with a particular prefix or not? Well, earlier, as before, we'll set the self.current as self.root, we'll get the current value, and we'll try to iterate over all the values in the prefix. Now I'm going to say, and this is a very simple check, I'm going to say if this character is inside of this self.current.child, if we have this character as a possible children, well, then that's fine. That is what we expected to have. Else, will return false. What I'm saying is, let's say that we are in the case, we have inserted all of these values over here, okay? And now I want to say, get me the prefix cx. Now the first thing we'll do is start off with this node, and then we'll try to look at all of its children, and we'll ask, hey, is C present inside of this dictionary? Is C present as a key inside of this dictionary? And so we only find characters A and B, and clearly this is C. The character C is not present here. So we can just return false right away. At the very end, however, if you are able to always keep on finding a child, then we can return true, saying that we did indeed find an entire prefix that matched, right? All of the characters in the prefix should match, and if they don't, we'll return false. So let me just clean this implementation up. We'll say if C is not inside of this, then we'll return false. Also, oh right, we want to set the self.current.child to of C, which is going to be equal to self.current. So this is exactly the same thing as we saw before, here and here. Let's do a quick check again, and this time we want to check for the function starts with. And let's say I want to search for the string AX. Is AX inside anywhere of the string, inside of anywhere of this tree containing only apple? This should return false. Sorry, yeah. Small issue, fix. What? All right, damn it. Fine. Cool. Okay, so our output is false and the expected is also false. Let me try a case that works. We'll say APP. Now APP should return true, and hopefully we'll see that as true as well. Okay, good, it works. So we are finally done with the starts with function. Now, how can we implement the search function? Well, the starts with function only checks for the prefix, but the search function checks for the prefix as well as one last condition, saying that yes, it should be a prefix, yes, but we should also have some word ended at this particular point. So we'll just return self.current.end. Let me run sample test cases. Sorry. Cool, we'll try to fix this. Oh, sorry, this is not prefix, this is word. Cool, this works. Okay, what's happening here? What's happening here is that we're saying, can you search for the word APP inside of this string, inside of this tree? So let's do a quick dry run. Okay, what happens here? So let's say we want to search. Okay, we have self.current as self.root. So currently we are sitting at this point. Fine. Then we want to iterate over all the characters in the word. So I'm looking for the word APP. So okay, that's fine. First we're looking at the character A. We're asking, hey, if A not in this, return false. So if A is A inside of any of these children. So we do find that A is inside of this children, which means that we're good to go. Current previously was this guy, so now we'll set the current to be this. Okay, we're now sitting at this particular value. Now we'll do this iteration again. Can you find the next character P? Can you find the next character P inside of its children? And we do find P inside of his children, so let's move on to this child. Now we'll go and we'll move on to the next iteration. So now we have again the character P. Is the character P present inside of this previously found node? Is the character P, and we do find that there is another character P over here. And at this point, we are completed with the search of this entire string. This completed with the search of the prefix. Now the only thing left to answer is whether this current value, whether this current P is an end position or not, if it marks an end of the word or not. And in this case, we do indeed find that this marks the end of a word because of this orange line over here, because of this particular value that we're storing here and this thing that we're saving. And in this way, we can finally think about now submitting this code. Let's check this out. Cool, okay. And yeah, pretty cool problem. Very basic, but it's always a good idea to know these different kind of data structures. So yeah. Anyways, if you like this video, be sure to give it a thumbs up. If you want more of it, subscribe. And as always, thanks for watching.